All right. Well, this week I'm very excited to finally get to sit down with Craig Ament, who is the CEO and founder of Arizona Thin Films, which you just told me. I hope I don't get this wrong, but I think you started in 2020, early 2020.
Yep, that's right.
Fantastic. So I'm super excited about this one because I know that thin films, much like optics, are everywhere. I know they're super important and I know nothing about them. I took a class in graduate school about them and it still just sailed over my head. Um, so what are thin films?
Yeah, so in short, without getting too technical on it, they're materials just like any kind of glass or basically dielectrics, right? So not metallics, although you can have metallics. But with the dielectrics, basically, if you can deposit a thin enough layer of material such that the wavelength of light, the visible light or infrared or whatever it may be, is actually comparable to that thickness, then you have an interference effect. So if you've ever seen, say an oil skid in a puddle in a parking lot, that's a thin film interference effect in all those different colors. So that's really all it is, just a very thin layer. And you can use different materials to build up different film stacks, and centering that interference at different wavelengths gives you either anti-reflective coatings or high reflector coatings. Beam splitters would be right in the middle of that. And then you can also have metallic mirrors. So those are basically not necessarily interference based. You just deposit a thick enough material that it's past the opaque point of that metal. So it behaves like any other metal. And then you put a dielectric protective overcoat on it to give it, so you can imagine thin metal layers are quite fragile. So you need to, if they're going to go out in the world, they need to be, protected with something. So
Right.
yeah.
And this is great because you've touched upon a lot of the questions I had listed. So I'm sure we'll be able to dive into them in greater detail. But one of my next ones is where are they used and kind of what are examples of it? You listed kind of the oil slick. And when you mention it, you specifically, I hope, correct me if I'm wrong, please, mean like that weird rainbowy kind of odd
Exactly.
effect, right?
Exactly. So you're actually seeing thickness variation of that oil or whatever it may be, grease or whatever, varying over the surface of that puddle. That's what you're seeing.
And what's happening? Like, why am I seeing green or blue or purple? I, why am I getting those weird striations of colors?
Yeah, so it's the thickness variation. So basically, it's some number of quarter waves essentially, and you'll have either more or less reflectance at different wavelengths depending on that phase thickness.
Okay. And so what are outside of oil slicks, what are examples that people would also be familiar with? One thing I was again reading up on thin films before this. Apparently, they're extensively used in cell phones, cell phone coatings. I'm fairly certain on my glasses I have an anti-reflective coating.
Yeah, yeah.
But what are some like
Absolutely.
common examples? I would say first in just like general life, and then I almost want to say I should use the opposite question in the world of optics and say what doesn't use thin film coatings. But yeah, I'll let you go ahead and answer
Yeah,
this.
that the second one would probably be a quicker conversation.
Yeah.
They're basically everywhere. The most common example, like you listed, would probably be eyeglasses. If you tilt your eyeglasses and look at the reflection off them, and the color changes, usually it's like a bluish or a pink or a green. Green's very common. That's it. That is a thin film interference coating,
Okay.
anti-reflective coating in that case. And then when you get the cool aviator sunglasses and they've got all the different colors on them, that's also a thin transparent metal.
And my ski goggles, the very cool ski
Exactly.
goggles that
Yeah.
all have, right. Okay.
Yeah, and so they deposit those at all different weird angles to get those thickness gradients, and there's a whole technique behind that.
And I think that that's, an important idea to get across, because you know, especially to people uh, outside of frankly like making and fabricating optics, it's not the material, it's the coating, right? That's that film that really is going to give you this um, unique kind of chromatic behavior that you might desire. And I love the idea that it touches everything from like, yeah, I'm skiing, you know, I want a certain look, all the way to very advanced optical requirements. So getting more into the optic side, you listed, you know, metallic coatings, dielectric coatings, and we've kind of alluded to anti-reflective or things of that nature.
Mhm.
Um, but why do I use a coating? And I know
Yeah.
that there are multiple uses, so kind of, you know,
Yeah, so it's so you know a good example, you know, if you're into photography or you've seen someone who's into photography, you know, they have these large macro lenses that go on the front of the DSLRs, right? Or you know, whatever your cameras are. And those might have, oh, gosh, I don't know, five to 10 lenses. I'm just guessing in those things. And at each surface, if it was all low index glass, which it's not, but let's just say it's all fused silica, which is a low index glass. And if you had no coatings on them, so each surface, you get about 4% approximately reflection. And put that through 10 to 20 surfaces. Basically, if the ghost images didn't kill you or ruin your image, your the throughput, the actual amount of light, everything would be so dark. Maybe you could get around that with software, I don't know. But basically, these lenses just wouldn't work without AR coatings. And that's in the fused silica case. So a lot of them have very high index classes where instead of 4%, you're getting 8 to 12% per surface reflection. That's significant, even if you go through one of those. So if you didn't have AR coatings on those, they just would not work. We wouldn't have these nice images.
you
National
just
Geographic.
you're just losing light, like it's just
Yeah,
hitting the front and bouncing away.
exactly.
So
So
that's one class, the AR anti-reflective coating class of films, and I waver on how in depth to get, but effectively that's a Fabry-Perot effect, right? Where it's of the right kind of cavity thickness. I shouldn't be trying to explain this. You should be the one explaining it to me, actually.
yeah, so basically it's what you're doing when you just focus on one surface. Say we have just a flat piece of fused silica, and we want to bring that reflection down from 4% to 0.1, 0.2%, something like that. What you have to do, so that fused silica is sitting in a medium of air or water, whatever it may be, but we'll just design it for air. So that's index 1, and then there's an index 1.45 approximately in the fused silica. So at that point, you have Fresnel reflection. That gives you your 4%. The anti-reflective coating, the job of the anti-reflective coating is to be an index step or index match those two together. So that's all that it's doing. It's much simpler for one wavelength. You can do that with 2 layers maybe. If you want the whole visible spectrum, 4, 6 layers, that type of thing. And it's a little bit hard to just explain verbally, but basically what you're doing, so when you design these things, you're looking at what's called an admittance diagram. And graphically, you can plot out phase thickness and the resulting effective refractive index, essentially. And when you design an AR coating, it looks like a spirograph kind of, and your goal is to go from this index 1.45 to index 1. And you do all these spirals, which represent different phase thicknesses of the layer, and then right back to 1.
and it's funny that you say that, because I was reading the Thin Films field guide and
Yeah,
saw these. I saw these spiral diagrams, and for I have a background in optics. I studied this for many years of my life, and probably should know more for how much time I've put into it, but that's beside the point. But I'm looking at these things and I was like, I've never seen a spiral diagram. This is not remotely familiar to me. Um, And it kind of, and we'll get into this, in a few minutes, but it speaks to the idea of, it's one thing to kind of do this first order, like, yeah, I don't want reflection, so I know I need an AR coating, but it's quite another to then design an appropriate coating,
Mhm.
which is where you come in. But before we even get to there, so AR coatings, uh, I imagine, however, that metal coatings aren't for anti-reflection. Maybe they are, but what's the primary use of those?
Yeah, so typically it's uh, usually a broadband high reflector type requirement. Like say you need 98% reflection from, I don't know, 1,000 nanometers to 2,000 nanometers. That would be very, very difficult to do with a dielectric coating. Um, Basically, you'd have to, so you could do it, you could absolutely do it, but you'd have to build a quarter wave stack around 1,200, and then a quarter wave stack around 1,600 roughly, and then maybe a third one to get out to 2 microns, and you'd have to index match those all together to make it nice and flat.
And these stacks each consist of several layers. Is that
Oh
accurate?
yeah, yeah. So
Okay.
probably,
So it's layer upon layer upon layer. It just gets unwieldy, I imagine.
yeah, it's
Um,
doable. If you have to do it, it is possible. But you could also do, say, a silver thin film. So maybe 50 to 100 nanometers of silver. If you pass the opaque point, that's going to get you up to your 98% there, no problem. Problem is silver tarnishes. So what do? Well, you have to add a protective overcoat, basically.
mhm.
So usually it's a half wave of SiO2.
And and so in my mind, kind of what it's boiling down to for thin films is, it's either going to let you pass more light that you want into your system without it reflecting away,
Mhm.
or it'll do the opposite. It'll reflect more light that you don't want passing through. Um, and I know one other area, just because I saw this on your website, was you can use coatings for damage protection. I assume physical damage protection, but also laser damage protection. Is that a fair description?
Yeah, yeah, and yeah, yeah, definitely. On the physical side, usually what people do is deposit what's called diamond-like carbon, or DLC. You'll see that referred to, and that can be for something, maybe the outer edge or outer surface of a lens assembly that's going, uh, in a less than lab type environment. Put it that way, and so they can deposit this, and it's very hard. It's opaque, or so it's transparent, very, very durable. Essentially, diamond-like durability.
And I just realized, for people that aren't familiar with coatings, or handling optics, we're talking about, you've said this, quarter wave or 100 nanometer, a couple hundred nanometers of metal. I mean, this is, for all intents and purposes, infinitesimally thin.
Yeah,
It's a, when you say thin film, that's hard to imagine how thin it is.
yeah,
Um, why doesn't it just fall off my optic, right? Like, how you, when
yeah,
you coat it, why doesn't it just fly away in the wind or something?
yeah, yeah. So that's a very critical thing. I think something that people overlook a lot. When in the textbook they draw these layers on the substrate, and they're planar, they're perfectly uniform, perfectly flat, and it couldn't be much further from the truth, right? If you look at SEM images of side profile of these coatings, some grow like tightly spiraled staircases right next to each other. Some have a big grain structure that's all mixed in. And the key is how do you get those to stick to a substrate? Right? Well, there are a couple different ways. Obviously, cleaning of the substrate has to be done, so you can't have fingerprint or grease or dust or whatever. That's one. When you pump down into the chain, or in the vacuum system, usually you give some sort of pre-deposition cleaning process. So for me, I'll use an ion source, and I'll actually, uh, ion clean, so bombard the substrate to be coated with oxygen ions for a predetermined amount of time, and that cleans up the surfaces or kind of functionalize it, so to speak. You get a lot better adhesion that way. And that's all assuming that the materials you've chosen like to adhere to each other. So for one example, we'll go back to silver. Silver is notorious for having issues adhering to a glass substrate. So there are certain materials that you can put down. Maybe it's a chromium, something like that. You put a very thin layer of that, and that acts as kind of an adhesion promotion layer. Yeah.
And helping in general to kind of protect it or things of that nature and hold
yeah,
it.
Yeah. So in the case of chromium on silver, that's just to make sure that the silver sticks to the substrate.
Okay, perfect. As a loose idea, I mean, how quote unquote sticky, I know that's not the right term, but how well do these things stay on? If I touch, and I'm sure that this depends on the coating, but if I touch something with my finger, for example, that has a metallic coating, will it come off? If I touch a dielectric coating, will it come off? I know that certain solvents will damage some coatings, but maybe that's for a different reason. So yeah, do you mind just commenting on that?
Yeah, so these metallic or dielectric, they should be very robust, and simple touching or cleaning with any isopropyl or methanol, that should be totally fine and totally fair game. If they do delaminate, there's something went very wrong.
You've either purchased it from the wrong person or you aren't using isopropyl.
Yeah, and I mean, you can certainly etch these things given the right solution, but as far as day-to-day use, they should be quite robust.
Okay. And I think the one scenario that I damaged a coating, I do want to defend myself a little bit here. It happened in lab, and I used liquid that was in an isopropyl labeled bottle, but was in fact not isopropyl. So I feel like I personally wasn't fully responsible for that, but but it was a unique moment of the surface started looking progressively worse and worse, and it was like something not right's happening here.
What was in the bottle? Do you know? It was just mystery fluid, or something?
I don't remember what it is at this point, but it was a solvent, but of like a higher classification. And I just don't recall like what it was. It wasn't ethanol, obviously. I just don't know. It was, something that not only should it not be used on optics, but it should be in a carefully labeled bottle, because I think it was like fairly toxic as well. So it's a fun day in lab.
There are some ideal ones.
So I think we've talked around it, and thus far you've said, look, there's metallic coatings, there's ceramic dielectrics, pardon me. They in general help to either get more light through, to reflect light you don't want. They can protect it. They're not going anywhere when you coat it. It's coated. So we've talked around the idea, but who needs these specifically in optics? And we kind of alluded to it at the beginning, but when do you need a coating?
Yeah, it's well, certainly anytime you need high reflection, so any kind of reflective telescope right there, you certainly need a coating. But really, more broadly, as optics gets more and more mainstream, generally people want to look at a certain wavelength and block a different wavelength or color of light, however you want to talk about it. There's really no other way to do that than by using thin film interference filters, basically. So if you want to, well, I'll give you an example. Even outside of traditional optics, right? A lot of, especially here in Arizona, a lot of windows, whether they're on commercial buildings, residential buildings, there are these low E windows. So basically, they kind of block the heat, right? That's typically a very 3-layer stack, and it's a little bit of titanium, some silver, not to its opaque point, and then another titanium layer, and that gives you kind of this, 60-70% transmission, and it cuts down on the heat, and it gives you a little color and whatnot.
Yeah, yeah.
It's, if you see any colored glass, it's usually some type of
coating. And I mean, you make a great point, that frankly, I think even, speaking for myself, let me say that instead, when I design lenses, sometimes it's hard to remember, is this going to be used outside? If it is, the sun is putting out a broad spectrum, and my detector might only be tuned for a particular wavelength, or I might only want a particular wavelength or band of wavelengths. Another area when I did research as an undergrad, it was in biomedical applications, and we strictly were doing what's called ratiometric imaging. So we strictly wanted 340 nanometer response, 280 nanometers, whatever. And coatings was the way to go. Like that's it. That's your option. In addition, I should add that it kind of blew my mind. The other day I was talking to the person I'd done research for, and being able to use coatings to be protective to the optics in the body was fascinating. Without going into too much detail,
there's a ton of applications, and I just when I thought I've heard it all, there's a new one comes along. So
right. And I just spoke with Eric Herman and Dave Akins, and they were talking about ISO 10110 and kind of environment testings, and it got around to that topic of acid damages optics, but you can put coatings on it. So in my mind, we said this at the beginning, I'm hard pressed to find an optic that doesn't need a coating, right, or at least that wouldn't benefit perhaps from it in its performance.
Right.
I said this before, I don't know much about coatings, but you really blew my mind when we talked a couple months back. When should I incorporate the idea of a coating into my design? Let's say I'm making a new system. When is the right time? Because before speaking to you, the right time was when I realize I need it at the end of the design.
Yeah.
I'll give Craig a call up and I'll say, oh yeah, just toss this thing on, right?
Yeah.
That's wrong.
Yeah. So usually, yeah. I mean, it's, if it's all flat glass at, normal incidence use, yeah, you can probably call me at the end. And it wouldn't make much difference. But the moment you start, putting these things in an imaging system, with high angles of incidence on the surfaces, you probably just want a little consultation about what's doable, or to at least have, an accurate expectation, I guess, at the start of what you might be able to achieve. Not to say you couldn't do it at the end, but you might be kind of penciling in your designer into maybe a spot.
And practically speaking, what is the impact? Let's say that it is super important to me for whatever application, medical or defense or space, whatever, that I get super low reflections in the 1200 nanometer band. What's the practical difference if I were to, at the beginning of my design, beginning in the sense of like, I'm going to have these general types of surfaces, probably this mini surfaces. I haven't finalized anything, but I kind of know the idea, first order design kind of thing. Sure. If I came to you at that point and worked with you for the coding process versus here it is, here's the design, the tolerance is done, we're sending it to the fab shop soon. What's kind of the different impact for me as a customer?
Yeah, well, so, if it's like, say, so there's always one element in these imaging systems that has, 45-degree AOI. They want it from 0 to 45, less than
and sorry, what does AOI stand for?
Oh, sorry, angle of incidence.
Okay.
So yeah, 0 to 45 AOI, less than 0.5% over this very broad range. And there's always the one element in there that has it all the time, which is fine. You can do it, but it is going to be more expensive because I can't batch it with all the other ones. I have to design a lot more, and it has to be a much tighter controlled run to be able to achieve that. If you don't want it to be expensive, and you want to batch it with all the other parts that have a lower angle of incidence, you can do that, but then you have to redo your drawing, basically, and just say for this one, 0 to 0.8% or something.
Is it more so controlling the angle of incidence in the design is what lets you do that?
So that's one thing, and then well, you can't really control curvature. That's just going to be what it is. But so
sorry, that's more so what I meant. So
if you want to, you always want to limit the angle of incidence if you can, or put it so if you had to have a high angle of incidence, sometimes it's just unavoidable. Right? I get it. Try to put that on a flat optic, flatter.
Right.
Because when you put a curved surface in a coating chamber, the apex of that lens is going to see a thicker coating than the edge. Just there's no way to control that. You can't cut a shield for that. It's purely 1 over r squared. The flux falls off according to that, right? So that variation in coating thickness, if it's extreme, has to also be accounted for in that design. So if you have a thinner, so you might be on spec at the apex, but you're off spec at the edge.
Right.
Which is tough because that's usually where the big angles are.
Exactly. That's where it matters. Yeah.
So now you're in a very tight spot.
Yeah. And one other thing, having done this, and I don't really consider myself a lens designer, but having kind of played around in that area, I think it can be very helpful from a customer standpoint if you can at least internalize, maybe we do have to have a high angle of incidence surface, and maybe we do have to have really tight tolerances for the coatings, but incorporating that into your budget early is a lot more helpful than going through the whole process and saying, I've done the design, I've done the tolerance, and it'll be costly to make this, and then realizing, oh, I have to get coatings, and because I've pushed it to the end, I have no budget for this, or I have to make a budget and it's going over. So I think kind of getting that information early is obviously helpful.
Yeah, I think that's the way to do it. Even if it's not a formal quotation, to say, hey, what do you think about this? I've done that for customers before. Not every company can have a coating person on staff. It can be tough. So yeah, I think early and often communication is always always a positive. So
well, and it's I don't exactly know why. You and I kind of mentioned this earlier, but in our months ago when we talked, but communicating with the thin film person isn't a thing. Too much in my experience, like especially early communication. I just don't know why exactly. It should be, but
yeah,
hopefully.
Yeah, I think maybe maybe they have enough problems and they don't want to hear about thin film problems.
Yeah. Hopefully this podcast can help nudge a few people. Craig is very nice to talk to. So the earlier you speak to him, the better your design process will go. So we've mentioned angle of incidence quite a bit. And in fact, you very generously answered a question on our forum recently that someone was asking, if I have a collimated beam, it's going to come in, and if it comes in at some funny angle, a high incidence angle, is there any downside to that? Do you mind kind of addressing that here as well?
Yeah, I mean, it's not really a downside per se, but basically what I told them is, as you go to higher angles of incidence, even forget thin film interference for a second, just, we have polarization splitting. So the Fresnel reflection for S and P, they diverge quite a bit. So that's just the side, even leaving out the coating. Now, when you add an AR coating in it, designed to work at, I think it was like 50 degrees, something like this, you're going to have a similar issue. So the P reflectance is going to be low. You kind of get that for free because we're approaching Brewster angle, basically. The S is going to pick up quite a bit. So then it's this balancing act where the effective index of your materials for S and P are going opposite directions, but you're on your admittance diagram and you're trying to get back to 1, right? The index matching condition. So the effect on that is that it's not going to, it'll be an anti-reflective coating because, the glass at that, 50 degrees angle of incidence, I wouldn't be surprised if our average was like 15%, something like that, just off the top of my head. But, at normal incidence, an AR coating could easily, over the bandwidth they were talking about, could easily get you under 0.5%, easily. When you go to 50 degrees, I mean, I just did a quick design. You can probably do better. I just did a very quick one. And I think our average was around 1.5%, something like that, where the P was down by probably close to that 0.5%, but then the S was about 3.
And that's a mind-blowing shift. That's a huge benefit. So
yeah.
If that's your goal, is to kind of reduce that R average.
Right.
So, I probably should have asked this earlier, but and I think that you demonstrated it already, but you have a company, Arizona Thin Films. I think it's in the name. You do thin films, but why would I come to you?
Well, it's so what I try to do is kind of pull back the curtain on the mystery of coding, so to speak. I like talking to customers about their application, and I try to be pretty candid about what can and can't be done, things like that. And also it's always kind of cracked me up in this industry. So evaporative coating has been around, long before I was born. People were doing this, so it's a very, very mature technology. And even today, people are still very, secretive about their designs, and they won't share what materials are in it and all these different things. And I always got a kick out of it because even if you've only been doing it a week, that in terms of material choices, say in the visible, there's about 6. And 3 of them play nice, and the other 3 are a pain to evaporate. And so, I could probably guess materials people are using. I could probably look at a scan and get a rough idea of how many layers it is. But something I hear from customers all the time is, this is going out into space. Are you able to share what material? The customer wants to know what material. Oh, yeah, of course. Yeah, tell them.
Yeah,
there's only so many ways to do this, and there's not a lot of IP in evaporative coating.
Right.
So I try to be open about that. It's really, they're not. So, and that's the thing, even if I published my designs on my website, it wouldn't be that useful to somebody because my coating materials are going to be different than the next coating house, like slightly.
Right.
So they still have to re-optimize the design a little bit, and maybe they couldn't get as high of an index or low of an index or whatever it may be. They'd probably just go redesign anyway.
Right. It kind of feels like a secret barbecue sauce recipe.
Yeah.
I can probably guess the main stuff, but any person that tries to make it would have it taste just a little bit different, right? Because of these very particular things.
Right.
And I think that's fantastic, though. I mean, you've discussed this, and I've heard actually from other people who have worked with you, that having that opportunity to talk through an area that for most of us is totally alien, is super helpful because it's kind of like, okay, I can wrap my mind around why this is hard or what we can do and kind of put a little box around it.
Yeah.
So what services do you provide?
Yeah, so we do custom optical coatings basically. I don't offer like a standard, a catalog type of specification. I played around with that a little bit, but ultimately everybody has an idea what they want. And so, yeah, we do all the in-house design, we can do prototype quantities up to high volume. It's custom optical coatings basically from the UV to the infrared.
And how often, not how often, but what's my expected, on average turnaround time? And I know that this heavily depends on lots of things, but just kind of on average, if I came to you, how long would it take, for example, to say, here's perhaps reasonable coatings, and then additionally, here's actually a coated thing?
Mhm. Yeah, so for quotes, I typically turn around at quotes in like 24 hours, unless it's a very involved design. I can typically turn those around pretty quick. As far as turnaround from when I get the parts to when you receive them back coated, a couple things play into that. So if I can get the order ahead of time, I can start doing test runs.
Mhm.
You always do test runs. Just the value of the product going in is too high to have an oopsie, right? So you always do test runs. That can take a little bit of time, and it has to fit in with the current workflow. On the other side of it is the tooling. So when these go into the coating chamber, you have to hold them somehow. And typically, uh, it has to be pretty precisely made because
Yeah,
you want to hold a very large thing just on the edge, a millimeter, which can be done.
I'm picturing you physically holding something
Yeah,
in the chamber and
yeah,
hoping, okay,
yeah,
everything will go
yeah.
well.
I put my spacesuit on and we go in. But yeah, so the tooling is can at times take a little bit of time, but if we have tooling in place, or we can relax clear aperture specs. So maybe if I can get 2 millimeters aside instead of 1, I can probably use existing tooling. That can come together pretty quick. I would say most orders turn around in about 2 weeks.
Oh, wow. So that's,
Is usual.
to me, that's
Yeah,
incredibly fast.
yeah. So 24-hour is possible, but that has to be something I've done before, and I have to do minimal testing.
Mhm. And man, I love this conversation because I have so many questions. And so how do you coat something? I mean, you mentioned evaporative coating. I know that there's I'm going to get this wrong now. The spinning process where you get kind of a filament a filament off, and probably more. But yeah, what is the process for coating?
Yeah, so basically what we do is the parts go up into the top of the chamber and they're spinning around. And you do that for uniformity, right? And the reason why you do that is at the bottom of the chamber, you have little sources, whether it's an electron beam source or a low voltage source, basically a little pot, and you heat it up. And there's a phase change. So the coating material is in your bucket or whatever you want to call it. And it heats up enough that it undergoes a phase change. Remember, this is all in a vacuum. So when you have this local phase change, it's a high pressure of the material here and nothing out here. So you have diffusion. So it diffuses in the whole chamber and coats everything inside within line of sight for most materials. We'll keep it simple.
I was going to say, I'm sure that the particle modeling is more complex than that, but I appreciate keeping it simple.
Yeah. And so you rotate around so that you average through the variation in the plume.
And so they're upside down in this scenario.
Yeah.
Okay.
Yeah.
Okay.
Yeah. So the surface to be coated is looking down toward the center of the chamber, and we're kind of spraying it with material.
Mm-hmm.
That's one way to do it. A better way to do it is to also have an ion assist. So you get very dense coating. So what happens is when you evaporate this material and it goes through a phase change, it has very low energy. Like I think 1/40th of an EV of an electron volt is the energy it will arrive at the substrate to. So it sticks and it just stays there. It doesn't rearrange. So what can happen if you don't give it more energy, either through heating the substrate or with an ion assist, you have basically porous coatings. So they're not densely packed. They're just kind of like in a room, say at a party where there's, everybody kind of spreads out to fill the space, and it's not densely packed people, right?
So it's like a middle school dance, right?
Exactly.
Everybody's keeping it, yeah.
Exactly. So why is that not good? Well, two things. It may not adhere well because you kind of have like a loosely packed coating sitting on your surface. And then when you take it out of the vacuum, what you can actually get is water seeping into those pores in the coating. And remember, we had some index refraction film with some fraction of air, which is index 1, and whatever the n of the index of refraction of your coating or your film is. Now a week goes by, and now that 1 is now filled up with index 1.33 or water. That's a significant difference in your optical thickness of that film. And what that will do is it will shift your film. So your AR coating that was great at this wavelength is now 4 or 5% of scale, which may or may not be what you wanted. So how do you get rid of that? You can either heat the substrate with radiative heaters, big lamps, basically, and that's okay. That will give enough surface energy for the evaporant to kind of redisperse into a more tightly packed configuration, or you can use an ion source. And that has kind of two effects. So I use an oxygen ion beam. The reason being is because I deposit a lot of oxides. So SiO2, TiO2, aluminum oxide, so on and so forth. So that does two things. There's a kind of a billiard ball effect. These very energetic ions pack in the evaporant material, but they also perform kind of a chemical function. So they're ensuring that you get the right stoichiometry, right? So TiO2 is a good example. That's a common high index material that's used in optical coating. And you can get anywhere from 2.3 to almost 2.5, maybe even a little lower than 2.3 index. So that's quite a big range. It has many oxide states, right? If you set your ion source correctly, which you do at the beginning, way before you ever make any actual coatings, you design a nice stable process so that you get a very stable TiO2 in terms of index and density. And so that's the function of how we coat. And then there's a lot of bells and whistles in there as well.
Sure. And it's and it's funny to me because at least in the evaporative coating one, I mean, it's something that everyone can readily imagine. It's effectively like, yeah, you take a spray paint can, you spray something, you're depositing these particles on it. It's just that for thin films, you've taken it to an extreme level, let's say, right? Like it's astonishingly accurate and difficult to do. And the ion one, I can't even think of a close analogy. The only thing that popped in my mind was I had put that white coating on my roof a few years back for Arizona for the heat. And it's a latex material. And I had to spend a lot of time going and cutting away bubbles because when they had done it prior to it being my house, there was water on. And like you're saying, I know that this is a fully different scenario, but effectively it turns out that water, when you're trying to get an even layer, ruins everything. So especially in ion coatings. So how, I gave a trivial example, right? I'm spray painting something. How accurate are these thin films?
Yeah, so depends how you monitor. So inside the chamber, you can determine when to end a layer one of two ways. One way is using a quartz crystal monitor. So you actually have a very thin quartz crystal disc in the chamber, up kind of close to the parts. That's usually in the center of the chamber. And there's an effect, it's basically a piezo effect. When you deposit material onto these crystals, and I should back up a little bit. These crystals actually, they're kind of a resonant cavity. So they have a certain frequency put on them, 5 megahertz, 6 megahertz. And then there's very sensitive electronics measuring that frequency in real time. And when you deposit material on the crystal, that dampens the frequency. So the frequency decreases or changes. They can go different ways depending on what cut of crystal you have. But suffice to say, that frequency change, if you measure it in real time, and then you make an assumption on the density of the material that is being deposited on that crystal, you can come up with a thickness or a rate of evaporation, and then integrate and get total thickness, right? So that technique, if it's properly calibrated, you can get about plus minus a percent, plus minus 1.5% of physical thickness.
Okay.
So if you have a 100 nanometer layer,
you can get 1 nanometer.
Yeah, for a very well calibrated process.
Sure.
The other way is, and so that's kind of an indirect, because you're measuring mass, but the key there is, so the property we care about is optical thickness, right? We don't really care. It's almost a philosophical point. How thick is the film? I want it to be the thickness times the index. And if either of those change, it's an error. So that's where the calibration of your process comes in very closely. You have to make sure that thickness correlates to that index to give you the physical thickness. So if your index drifts, that's an error as well, even though your quartz crystal read the right thickness within reason. Right? And
where do you get that index drift from?
So yeah, so when you start up a new system, and periodically you check it as well, you spend a lot of time just evaporating single layers, very couple quarter waves of your high index material and your low index material. And then you put them on a spectrophotometer. So you measure reflection and transmission, and you look at those curves and also position in the chamber, because it can vary over that. And you look at those curves and you develop, or you calculate what the dispersion is, or what the index is. And you look for things like variation in index with thickness and absorptions, things like that.
Right, because it's probably not going to be linear effect type of thing.
Yeah, there is, like TiO2, for example, below 400 nanometers, it starts absorbing, and you can see that. So you wouldn't use that, I would say, for a 355 nanometer, for example. You'd have to use a different high index.
Right. So you're effectively saying, okay, I can deliver in a highly calibrated system, of course, an accuracy of plus minus a nanometer or something in that range across your surface. And that's really on the scale of kind of like atomic layer thickness.
Yeah,
but
it's a little bit bigger, but yeah, it's close. It's not far off.
It's in the ballpark, right? Which I only say that because it's mind blowing. There's so many things about optics that are just crazy, but that's another one which is definitely insane to me. Does it matter how uniform it is? So does it matter if I'm sure it does, but so why don't you tell me about that? Like, what kind of uniformity do you get?
Yeah, so uniformity, it's on a flat substrate. It's similar. It's about plus minus a percent, plus minus 2% at the most, and that all kind of gets rolled in to your tolerancing when you do a design. So you can always get a great design. The question is, can you make it? And that's where you start having to factor in those variations. And so that was for a flat piece. If we have a curved piece, so a sag with a lens, right? In the system I have, and it's all very system dependent, a 1/4 inch of sag is about equal to 1% of
Okay. Okay.
from apex to edge. So you have to factor that in.
Right. And a 1/4 inch is pretty significant.
Yeah, yeah, it's pretty, yeah. You don't often see sags to that degree, but
Yeah. If I'm dealing with one of those condenser lenses, maybe that's where it's
right.
a little bit trickier. All right. Well, as I told you, I asked people what questions they have for you, and people had questions, which is fantastic. So I'm going to kind of rapid fire these off if you're up
Okay.
for it.
Sure.
Perfect. 2 people asked this. Where is the thin films industry going?
Oh, that's a big one.
Starting with a small question, right?
Yeah, no, I think if you're using light, coatings are on it.
Okay.
There's just no way around it. So I think a similar question with a similar answer would be, where is the optics industry going? Now, specific to coating in itself, we're all familiar with evaporative coating or sputtering, things like this. I think that probably the future for actual optical coating is going to be something different altogether. It's atomic layer deposition. And basically they make fantastic films. It's these 2 precursor gases that you feed into a chamber, and basically it's a self-limiting reaction. So if you want to deposit aluminum oxide, a 1/4 wave, you put in this precursor gas, and some chemistry happens, and it forms a perfect atomic monolayer of aluminum oxide. Well, can't really be atomic if it's a compound, but
right.
You get the idea. And so then you alternate precursor gases, and it's aluminum oxygen. And you get, if it's done right, and there's a lot of know-how there, you can build up kind of a very pure, very controlled thickness film. And it's been around for a while. It's not exactly new, but now I'm starting to see actual commercial systems that are coming out that you can purchase this type of equipment. I think a lot of what did it started getting more widespread use. So the precursors, these gases, are now a little more affordable than I think they used to be.
Right.
And so why would you use this technique over evaporative or sputtering? Well, say you have a ball lens, right, and you want to get that coated. Well, I can only coat one face. I can't coat, I have to flip it. And well, with ALD, it will coat everything in the chamber.
Yeah.
So you will get perfectly conformal coating.
And that severe departure due to the curvature,
it won't matter.
It's not right.
Because
how you hold it, how you hold that ball lens is might be a little tricky, but
yeah,
that's
so you have to hold it somewhere. But yeah, or like say you want to coat the inside of a test tube or something, and that would be totally impossible with evaporative or sputtering.
Right.
You can't.
You need that direct line of sight.
Yeah.
And you and I have, you mentioned this, and I've as well said this, a lot of systems, it's not anything too crazy. It's not, super curved or whatever, but we love to talk about this in the optics industry. God knows I've used the sentence many times in papers that, free form is coming and it's shifting everything. And you are starting to get crazy surfaces with all sorts of highly varying, highly steep slopes across a surface, or systems that you might, as you said, need to coat kind of the inside of something. So, so that's super exciting that this is coming.
Yeah, so I think it's coming. I think there's always going to be a place for evaporative coating and sputtering and things like that. But and it's such a mature technology.
Right. Well, and I think that a big part of it is, this is why people should come to you, right? To know what is the appropriate approach for my specific need. It's all too tempting to say, hey, I heard of this, brand spanking new thing, I better use it, and to not realize it might not be the best result. The next question, this again, I think is probably a large one. What are the basic rules of thumb for someone using AR coatings in imaging applications? I can throw one out
Okay.
while you think about it.
Okay.
One of my better lessons learned, I was presenting a system when I took Matt Dubin's class, and Richard Pfister was on a committee kind of giving us feedback. And for those who aren't familiar, Rich is, he's the guy. He's the guy for stray light. Incredibly smart in the area of optics, and I'm sure in other areas. And I had chosen an aspheric condenser lens, something high curvature. And the purpose of this project was I need to find an LED. I know the wavelength. I need to find it in a wide field of view. I'll just use a coating, right? I'll use a filter and it'll be great. I can get a bunch of light and I'll knock out everything that's not my wavelength. Unfortunately, Rich was very nice. He pointed out, put the filter before your lens. Don't do it afterwards where light's coming in really at a steep angle. So that's one lesson.
Yeah, yeah. I mean, so usually it comes down to something like that, right? Trying to move the coating into a point in the system where it doesn't have to work as hard or be as sensitive to give you the performance you're looking for. And really, I mean, it's tough for me to boil down a list of rules of thumb. Probably if I thought about it, I could maybe come up with some. But really, the earlier you can get something in front of a coating designer and have them take a look at it and say, hey, am I close? Is this just totally out in left field? That would be kind of my number one rule of thumb is call the coating guys.
Yeah, call them earlier. And that probably addresses the first point, because they would be the ones to tell you earlier.
Yeah.
Let's put the coating on something less steep if you can.
Yeah. And that especially with filters.
Right.
You almost always want those in collimated light, depending on how narrow band it is, right? If it's one of these like Raman spectroscopy filters, yeah, that cannot go on a curved surface. There's absolutely no way.
Yeah.
If it's only a couple millimeters wide, but.
And the reason for that, I should add, is it shifts as your angle of incidence. A lot of these are designed for an angle of incidence. Typically, if you find a pre-made filter, it'll be for 0 degrees angle of incidence. And as you shift away, that shifts the wavelength that it's actually operating at.
Yep.
You know more than I do, but we don't need to get into the weeds on that. Why would I ever not want to coat a lens? I think it's also fine to say you always want to coat a lens. But
yeah. Well, yeah. I mean, that's my default answer. I'm just trying to think. I mean, maybe, if throughput is not necessary, or you're using it like a pick-off mirror or something like that, where you want the 4% reflection, maybe it's you're measuring power on that or something. I suppose there are some specialized setups where you wouldn't want a coating. But as soon as you go to any angle of incidence and you're using a polarized source, it kind of drives you to you need one to a coated solution. Yeah, typically. And there are probably applications where you don't want one.
Right. And the only thing
come to me, so
yeah. And the only thing that pops to my mind is if you did it wrong, if you didn't go to someone like you and I don't know how you do this, but you coat your own lens and choose the wrong material, and it happens to not play well in your environment. But that's literally just doing it poorly. So I don't think that applies.
Yeah, I mean, I guess if there was like a really, say a substrate had to go in an acid solution or something like that, something that was going to etch.
Right.
But that's hard to imagine too, because the coating materials chemically are usually pretty similar to the glasses. So if it will etch, in a lot of cases, like for oxide, if it will etch the oxide coating material, it's going to etch
the glass as well.
So yeah.
All right. The next question was, this is a two-part question. So first of all, is there anything you wish you had known before you started Arizona Thin Films? I assume about starting a company.
Uh, yeah, well, I spent a lot of time planning it, so I didn't know COVID was going to happen, but it worked out anyway. Um,
And do you mind if I ask kind of what does that planning process look like? So both of us have started companies, and I spoke with students somewhat recently and highlighted the same thing: plan, plan, plan. If you want to start a company, it will really save you a lot of headaches. But what was that process like?
yeah, so for me, with my company, it's very equipment intensive, right? You can't sit at a desk and make a coating. So, for me, it was very much a cost basis game, right? A brand new coding system is $1 million. Well, I'm not going to spend, I don't have $1 million. So I had to get really good at kind of finding gems on the used market. I actually got one it was basically at auction. Um, it was an IBM coding system. It was used in the semiconductor facility. They ordered it brand new, $1 million. They got it delivered, did the acceptance testing on site, and then the fab closed down.
Wow.
So but you can't make that happen. You know what I mean? You just have to be opportunistic when it comes up, and
Mm-hmm,
you have to know the equipment well enough to be able to go on site and look at it and say, yeah, this is a good deal. I'm not getting screwed. So that was pretty key. And then with the metrology equipment, same thing. It's very expensive, but if you go in the used market and you know the equipment, you can get very, very, very good deals.
Yeah.
So for me, it was getting that together. So you have you have to get your costs down as low as possible to enter, but then also have the working capital to stay in business.
Mm-hmm.
Like, you can't just be open for 6 months and hoping you're going to hit it in 6 months, because that's not going to work. So you got to have a long runway. How do you do that? You lower your cost basis.
Right. And I think that this gets at the second part of this question. The person asked, how did your education help or not help the startup? And I want to add on to that. In my experience, I knew optics. I have the background of optics. I did not know business. So, with respect, this is a question for you, but just I'm answering it as well. With respect to my education, I had to really scramble to learn business. The wonderful thing I found was there's a lot of free materials or even books or whatever about starting a business that I'll not only do I highly recommend, I'll also link to. There was one course in particular on MIT that was free. So
nice, very nice.
uh,
Yeah. So for me, it was my parents started businesses. There's a lot of business owners in my circle, kind of. So that was invaluable, because when you start out, it's no one holds your hand. And you can make a lot of choices, and you can make a lot of good ones and a lot of bad ones. And
you live and die by your choices in a unique way with a startup, I think.
Yeah. So
uh, okay, well, and all right, well, so we'll get to the next one. Same person, but they asked. First of all, they stated what is undoubtedly one of the most true things I've read to date. Thin films can be a mysterious subject. You've demonstrated a deep knowledge of vacuum systems, physics, chemistry, material science, and optics. So mysterious subjects, almost underplaying it. But this person was curious to hear, what are the common misconceptions that you might hear from people who need a coding or think they don't need a coding?
common misconceptions.
I think
Well,
I think one would be you can come to you at the end of the project and it won't
yeah,
have any impact.
yeah. I think it, it's always better to get someone to look at a first principles design earlier than later. And that's kind of tricky, right? Because when the drawings are released, depending on the company, they're not changing them. So at that point, the price has to go up. Another misconception I would say, I think people underestimate how hard it is to, or how hard it can be to hold some of these optics in the vacuum chamber, right? So they're spinning up top. It's heating up, from room temperature to 100, 200 C, things like that. So that if you have an 8-inch optic and you put a 1 millimeter, 8-inch minus 1 millimeter clear aperture, that's really tough because I have to hold this thing somehow. And I can put it on that ledge, but you're really playing with fire because if something jostles,
Yeah, yeah.
you're playing with fire with that. So, usually you want, so 90% clear aperture is like standard. 95's reasonable. We can do it. When you start to go 97, 98%, it's like,
Pushing it.
I can do it, but you're taking a lot of risk. So my question would be, do you need that extra couple percent? Or
Mhm.
can we just safely hold the optic? Because there's a chance if you make it too small, do the coating, I open up the chamber and it's a pile of glass on the bottom of the chamber. And we don't want that. So, yeah, I think clear apertures sometimes get overlooked.
Okay.
Yeah.
The next question was, what is the best way to specify coatings when you don't have access to the prescription? Um, and the person went on to say, sometimes a coating structure can lead to variable reflectivity outside the bands of interest. So
Yeah. And then which is fine if you don't care about those bands. But if you think they might be an issue, then you probably got to broaden your spec range. But the broader you make it and the closer to 100% reflection or 0% reflection, the more difficult it's going to be.
Okay.
Yeah. So that, again, every coating house will tell you a little bit different of what their specs might be. You know what I mean?
Right.
Because you can make a super low AR coating over a broad range, but it may take a month or two of testing, and all the while you're running other jobs. So you're not working on it every day for 2 months. You know what I mean?
Right.
Yeah.
All right. The last community question was, what are the different considerations for indoor lab applications versus harsh outdoor environments?
Yeah. So usually you handle that with either a humidity test. You put a witness sample in a humidity chamber, whatever the profile may be of humidity, temperature, time, and you pull it out, and then you do an adhesion test, there's a cellophane tape test, and an abrasion test, and the coating should survive that. It's kind of an accelerated lifetime testing. That's one. There's also various types of temperature cycling, salt fog. There's a whole slew of mill and ISO specs relating to environmental stability of optical coatings. And if you're going to be in an environment like that, then you may want to tack on a temperature or humidity specification. But usually, at a minimum, whether this is on somebody's drawing or not, I'll test for adhesion, which is just a tape test, because that's whether you put it on the drawing or not, you want your coating to stay on the part, right? And then I'll do moderate abrasion for anything except a bare gold.
Right.
Obviously, bare gold's not going to stand up to any abrasion, but it should still adhere. That's the
right.
And then beyond, if it's going to be out in a less than ideal environment, then you may want to look at those other mill and ISO specs. And that can be added to the drawing and tested and things like that. So
And then I just have one, which is for anyone interested in getting into the thin film space. How do you get into it? How do you learn about this area? And, if you want to work in it or whatever, go towards that.
Yeah, it's a pretty, nobody gets at least I'm not aware of anybody that gets a degree in, thin film engineering or something. I guess material science would be the closest one.
Yeah.
But that's pretty broad too. So, that could be, you know, getting the paint to adhere to cars. That's a tricky problem too, and it falls in, the more the material science side. Um, Really, if you want to do optical coating, you have to go to a place that's doing optical coating, and
Mhm.
you'll learn on the job. Because if you try to, there are textbooks and things, but there's very little published about like process know-how.
Mhm.
You can design a great coating, but now go to the chamber and make it with good adhesion. It doesn't shift, it doesn't absorb, things like that. There's a lot of hands-on know-how, and I think even if someone wrote a book, it wouldn't be applicable broadly because every chamber is a little different.
Right. Right.
So it's very much a hands-on learning experience.
Well, and I think back to most of my most of my education, I feel like where I learned how to do something were the labs, and there were no thin film labs.
Yeah, it's
So
time-consuming and expensive.
yeah, yeah,
Yeah, it would never
uh,
fit in a 3-hour lab session.
right, right. So the real way is, if you're interested, reach out to someone doing thin films and see if you can get a job and kind of
Yeah.
learn there.
Yep. Yep.
Perfect. Well, I don't have any more questions. So,
No,
are there any other areas or topics you want to discuss that I left out?
no, I think that was good. Broad.
Perfect. Well, for our listeners, Craig runs Arizona Thin Films. You can look that up, but I'll also be sure to include your company in the show notes. And Craig, thanks so much for being a guest.
Yeah, thank you. Thank you, Logan.